Hi everybody, we're going to be talking about two more gas laws, Dalton's law and Graham's law. We're going to start with Dalton's law. So Dalton studied gas mixtures. So an example of that is air. Air is made up of mostly nitrogen. It has oxygen. It has some carbon dioxide, some water vapor, some argon, and other things. So he said that the total pressure of a gas mixture is equal to the sum of the partial pressures of the part. So P total pressure of air, for example, is going to be equal to the partial pressures, the pressures that are due to each individual gases. So if this was air, the total pressure of air would be equal to the partial pressure of the nitrogen plus the partial pressure of the oxygen plus the partial pressure of carbon dioxide plus the partial pressure of H2O vapor and argon and so on. So here's air like we said. So 78% of air is nitrogen. The pressure that's due, the collisions that are due to the nitrogen are 79.11 kilopascals. Oxygen is 20.95%, so almost 21% of the air. And in kPAs, it contributes 21.22 kPAs. Carbon dioxide, 0.04, argon and others are 0.95. So if you add all the gases up together that make up air, 100% of air, the pressure at sea level is 101.32 kPa. So this is a little bit of trivia here. At the top of Mount Everest, the total atmospheric pressure is only 33.73 kPa, so only about a third of what the pressure is at sea level. The higher you go, the lower the atmospheric pressure. So the partial pressure up on top of Mount Everest is only 7.06 kPa compared to 21 kPa at sea level. To support respiration, the partial pressure must be 10.76 kPa. So since, the oxygen is too low at the top of Mount Everest, that's why hikers that go up there need oxygen tanks. So let's try a problem. It says, what is the total pressure of a mixture of gases containing oxygen, hydrogen, and water vapor if their partial pressures are given, respectively? So you're going to say that the total pressure is equal to the partial pressure of the oxygen plus the partial pressure of the hydrogen plus the partial pressure of the water vapor. So P total is equal to 120 kPa plus 94 kPa plus 137 kPa. And with sig figs, that is 350 kPa. Now, what are some other, this is pretty simple, it's just addition. What are some other things I could do to make it a little bit harder? I could give you the pressures, the partial pressures in different units. You have to convert them before you add them up. Or I could give you what the total pressure is, maybe the partial pressure of oxygen and hydrogen, and then ask you what is the partial pressure of water vapor, so you have to subtract. The last thing I could do is I could tell you, hey, for example, oxygen makes up 20% of air, and the total pressure of air is, let's say, 101.3 kPa. What is the partial pressure of oxygen? So if you want to do that, you'd say oxygen is 20% out of 100. So X out of 101.3 kPa. That's one way to do it. Another way to do it is to say that it's P total times the percent. So P total times 0.2. These are all the different types of questions I could ask you about Dalton's law. So it's a pretty straightforward law. The sum of the parts is equal to the total. Let's take a look at Graham's law next. So Graham studied the movement of gas particles. He studied effusion and diffusion. So let's define those real quick. Effusion is the escape of gas particles through a small opening or a small hole. So if I have a balloon, for example, and I poke a hole in it and the gas particles start to escape, that would be effusion. Diffusion is what we're normally used to. It's the movement of gas particles through another gas. If I were to spray perfume at the one end of the room and you smell it at the other end of the room, that's because gas particles diffuse through the air. So either one, effusion or diffusion, is movement of gas particles, and so that's what Graham studied. And here's a picture of diffusion. So here you have a container with a small opening here, so the movement of gas particles through that opening would be diffusion. Now, just to review, we know that as kinetic energy increases, the velocity or the speed of the gas particles increase, and that kinetic energy is related to their root mean square speed. What that means is that kinetic energy is equal to half mv squared. Remember we said m is the mass, and then v is the velocity of the particles. You do not need to know this equation, but from this equation we're going to basically derive Graham's law. So let's say I have two gases, and they're both at the same temperature. What does that mean? Well, it means that they have the same kinetic energy, because remember, kinetic energy is related to temperature. So if I have two gases at the same temperature, that means they have the same kinetic energy. So half mv squared of one is equal to half mv squared of the other. So let's say I have some CO2 and some oxygen, and they're both at the same temperature. That means they both have the same kinetic energy. But remember, kinetic energy is not only related to the speed, it's also related to the mass. So if both of their kinetic energies are the same, but CO2 is more massive, has more mass, then that means it has to be slower than O2. And so Thomas Graham noticed that the rate of effusion or diffusion is related to the molar mass. So he said, we're gonna derive Graham's law together here. You do not need to be able to derive it, but I think it helps you understand it better. So let's say you have two gases, gas 1 and gas 2, and they're both at the same temperature. That means their kinetic energies are the same. So kinetic energy of gas 1 is equal to kinetic energy of gas 2. We know that kinetic energy is half mv squared. So we're going to say half mv squared for gas 1 is equal to half mv squared of gas 2. Now each of those gases have a different mass. That's why we labeled it as M1 and M2, and different speeds as well, so 1 and 2. We can cross out these halves right here because they're on both sides of, that was an X here, sides of the equation. So you get that M1 V1 squared is equal to M2 V2 squared. Okay. Now if you rearrange this to put the M's on one side and the V's on the other side, so let's say you take this V and put it on this side, so it'd be V1 squared over V2 squared, so that's this one. And then you move the M's on the other side, so you move this M here, so you get M2 over M1. So if you do that, you get M2 over M1 is equal to V1 squared over V2 squared. If you square root both sides, so square root of this and square root of this, then you get the square root of squared, those cancel, so V1 over V2, which is right here, is equal to square root of M2 over M1. V1 and V2 are the rates of effusion or diffusion, or basically the speed of, or the velocities of the particles. M1 and M2 are your molar masses. So basically what this is saying is that the speed of the particles is inversely related to the square root of the masses. And it's inverse because this is 1 and 2, but then this is 2 and 1. So the higher the molar mass, the slower the particles are, which makes sense. You know, if you if you can imagine, for example, when I was pregnant, I had gained 70 pounds. I was way slower with extra 70 pounds than I was without the 70 pounds. So the lighter you are, the faster you move. The heavier you are, the slower you move. And so that's what Graham's law is saying. The rate of effusion or diffusion of gases is inversely proportional to the square root of its molar mass. So again, the higher the mass, the slower the particles, and the lighter the mass or the smaller the mass, the faster the particles are. Here it is in a different form. So instead of V's, sometimes you see R's, R for rate as opposed to V for velocity. And then this is molar mass there. So R1 over R2 is equal to the square root of M2 over M1. Let's try a problem. So this says, find the relative rate of diffusion for the gases krypton and bromine. So since it's talking about rate of diffusion or effusion, you'd think Graham's law. So you want to write Graham's law, and you can write it with the R's or the V's, whichever you prefer. So R1 over R2 is equal to the square root of the molar mass of 2 over the molar mass of 1. Now, I actually don't like to write 1s and 2s. I prefer to write what the gases are so I'm not confused, so I know which one goes where. So I'm going to do that. So I'm going to say the rate of krypton over the rate of bromine, and don't forget bromine is diatomic, is equal to the square root of the molar mass of the bromine over the molar mass of the krypton. So I'm looking for the relative rate, which means I want to know what this ratio is. So I'm solving for this whole thing. So that is going to be equal to the square root of about 160. Each bromine is about 80 grams per mole. So Br2 would be 160. And then krypton is 83.8 grams per mole. And so this ends up being 1.38. Now I'm going to put it over 1 for now. It's the same thing as 1.38. But I just want to explain what that means. So we're finding the ratio of rate of krypton to rate of bromine. And we found out that it's 1.38, which is the same thing as 1.38 over 1. So this is saying if bromine moves at a speed of 1, krypton moves at a speed of 1.38. Or in other words, krypton is 1.38 times faster than bromine. So if your answer for this gives you a number higher than 1, that means that the gas on top is faster. If it gives you a number lower than 1, then that means that the gas on the bottom is faster. Other things I could ask you about this one, I could give you the rate of one of them and ask you for the rate of the other. So you can look up the molar masses from the periodic table. You can insert the rate that I give you here and then solve for the other one. All right, that is it for Dalton's and Graham's law. Have a wonderful day.